Hello everyone, welcome to MindSpan Education. We started looking at the different spatial probability densities function. Before we look at more special kind of probability density function, let's look at the important measurements or the quantities regarding the random variables. As we have seen in case of the discrete, what are those? Those are like expectations, variances. Similarly, we will be looking at in case of the continuous random variable. So the first quantity that we are going to see is the expectation or the mean of a continuous random variable. You at this point you must have idea what is this expectation. We have covered this expectation, what actually this represents in a very detailed manner in case of the discrete random variable. Point to note here, the concept or the idea that you have learned in case of the discrete random variable will remain same in case of the continuous random variable as well. What are the things going to change? You will observe that since it's a discrete case, we are using here the summation sign. Here it's a continuous case, we will be using the integral sign. Here we are using the PMF, here we will be using the PDF. Otherwise, the core concept, or if I have to take just an example, what this expectation, the concept of it will remain same in both cases. What is expectation? What does it represents? We have already seen, right, in case of the discrete random variable. So this expectation represents the average of the value we expect to see in a very large number of independent repetitions of the experiment. And how, so if this sentence seems still abstract to you, then I would highly recommend go and watch my previous videos in case of the discrete random variable regarding this expectation. Then you will have a good idea what actually this expectation is, what kind of measurement it is giving to us regarding the random variable, right? And at the end we have reached at the conclusion that this is the formula that gives us the expected value of a random variable. What is it? So what we do, we find the weighted average value. And how do we find? We just take all the possible values of the random variable and we weight these values according to their corresponding probabilities, and we sum over all possible values of random variable that it can take. The idea will remain same. Here now the summation will get replaced by this integral. What we are doing, we are taking each and every possible value and we are weighting this with the corresponding probabilities, right? So what is this? So if you see this fx dx, this is nothing but a dx will have the very little length, and this represents the PDF, that means this height, right? And we are integrating over all the possible values of these x, right? So overall, if you compare this to the discrete case, the same thing we are doing it, right? Since it's a continuous case, that is why we are using the integral sign, right? Again, the intuition of the expectation will remain same. What this expectation is, so expectation represents the average of the value we expect to see in a very large number of independent repetitions of the experiment. Here this formula is well defined, but this formula is not well defined. But for us, we will use such a way that it will be always well defined. But to just have on the safe side, let me write down this one also, that this expectation formula will be well defined in case of the continuous random variable when you integrate the absolute values of x corresponding to weighted corresponding to their respective probabilities. Then this integration should be less than infinity. Then we will say that this integral will be well defined, right? But you will not have to worry about this. You will not have to check if this is well defined or not, because we will be using such a way that it will be always well defined. Now let's look at the properties of the expectation. We will see in case of the discrete case, and we will just use the idea what we have learned in case of the discrete case, and we will rely on that idea, and we will just write the formula directly in case of the continuous random variable. So let's look at the few of the properties of these expectation in case of the continuous random variable. So we have seen that if random variable takes the value that is non-negative, then the expectation will also be non-negative. And if this random variable x takes the value that is in between a and b, then the expectation will also within this range that is from a to b. We have also seen the expected value rule, right? So let's say if we have a function, if we have a random variable x, and this random variable x, so this gx is a function of this random variable x. So this function will also be a random variable, right? And how do we find the expectation? We can make use of the expected value rule. So using the expected value rule, we have seen we can find the expectation of this function again. The formula will be same, whatever the value it will give times the corresponding probability, and we sum this term for all the possible values of x. This is what we have seen as the expected value rule in case of the discrete, right? And what will be the expected value rule in case of the continuous case? Again, the core idea will remain same. The summation will get replaced by integral, and the PMF will get replaced by PDF. So this is what the expected value rule in case of the continuous random variable. If we have to take the example, let's say if gx is equals to x square, then what's the expectation of this gx? We can make use of the expected value rule to find the expectation of this function gx, and that will be integral from minus infinity to infinity x square, right? We have also seen a very important property about the expectation. What is it? The linearity property. If you have a random variable, let's say x, and if this random variable x is a linear function, so let's say we scale with this random variable with a and we add b, right? Then the linearity says that if you try to find the expectation of the linear function, then either you find the expectation, so whatever you have done to this random variable, you have scaled, then added this value. And if you want to find the expectation of this function, so what you can do, you can simply first find the expectation value of this random variable x, and whatever you have done to, or whatever the function that has been applied to this random variable, the same thing you are going to do with this expectation as well. And this is only valid when we have, or when the random variable is a linear function, right? So we are going to also multiply this expectation with a plus the term b will also get added to it, right? And this linearity will again hold if we have the continuous random variable as well, right? Now let's look at the another quantity, that is the variance. What is this variance? What kind of measurement it gives you for the random variable, let's say x? So variance and its properties. So what is variance? We have seen, right? So variance is the expected value of square distance from the mean. This is what the definition of the variance. And we have also seen one more quantity, that is the standard deviation, right? So what is this standard deviation? So while calculating the variance, you will observe that this square term is getting there, right? So the ultimate unit you will get in terms of the square, right? But somehow we want to measure the distance or maybe other quantity, then we want to have a correct unit for that. So that is why we have defined this standard deviation, and this will be nothing. So standard deviation of this random variable x will be nothing but the root square of the variance, right? And if you are still not comfortable with these terms, right, then go and watch my previous lecture. You will have a better understanding of these terms, that what is variance, what is the standard deviation, right? We have seen one more property, that and again all these property will hold in case of the continuous random variable as well, right? We have seen one more property, that if we have a linear function of this random variable, and if we want to find the variance of it, then that would be variance of this random variable x times a square, and there will be no effect of this plus b, right? And we have seen one more alternative formula of the variance, and most of the time we have used that formula to find the variance of any random variable, that is the variance of this random variable x. How we have found this formula? So we have found this formula by expanding this, right? So this is nothing but the expectation of the square of random variable minus the expected value का square, right? So we have already seen and we have a very good idea about all these formula, and the same things are going to apply in case of the continuous random variable as well, right? Now next lecture we will see, and since we have already looked at the probability density function of the uniform random variable, in next lecture continuous uniform random variable, in next lecture we will be looking at how can we find the expectation of this continuous random variable, continuous uniform random variable, and the variance of this continuous uniform random variable.